Page 4. The temperature of water as it cools to room temperature is modeled by the function, and here we have a function here. And we are going to put this in our calculator, of course, because that's what we do. We can figure out all kinds of things once it's in the calculator. Okay, and do you notice I put parentheses around the fraction? It's always a good idea to do. It's always actually a good idea to put the parentheses around the fraction and around the numerator and the denominator, especially if the numerator and denominator are something plus something, something minus something. There's all sorts of weird things that can happen if you're not really being careful with your PEMDAS. So now that we have that typed in, we're going to graph it. We can't even see most of it. It says actually to graph the function from 0 to 15. So let's adjust our window so that it goes from 0 to 15. And I think a lot of it's going to get cut off. So let's also do zoom fit. All right, there it is. Okay. X is the time in minutes, and f of x represents the temperature in degrees C of the water cooling to room temperature. Okay, so we sketch the function. It looks kind of like this. Okay, and it says calculate the temperature of the water after 10 minutes. How do we do that? Well, there's two ways. One is we could do trace 10. And it tells us that y is equal to, and I can't even read it because the cursor is like right on top of it. Okay, it looks like 27.9. Let's check on second table. We'll go to 10, x equals 10. 28.9 is the answer. Okay, so calculate the temperature of the water after 10 minutes. It's 28.9. How many minutes does it take for the temperature to cool down to 50 degrees C? Let's see. It's already cooled down to 35 here, so... Oh, there it is. So it's between 2 and 3. So there's a couple ways to do this. One is we could do plus 0.1, and then we could see a number that's a little bit better, like 2.7. And let's say we want to know even in more detail, with more precision, and then we'll change to 0.01, and then we can see that actually it's 2.72 is closer. Okay, so we'll put 2.72 minutes. Okay, and another way to do that, instead of doing this, if you don't really like doing this, which is kind of, it's not really an elegant way of doing it. The most elegant way of doing it is to put a second line here, a horizontal line with the y value that you want, 50, and then you graph it, and then there's going to be a intersection here, and the way you find the coordinates of the intersection is you do second calc intersect, and then you say first curve yes, second curve yes, and then you just, it doesn't really matter where you put the guess because there's only one intersection anyway. And then it tells us that the answer is 2.72, comma, 50. What do you know? 2.72. Same answer, right? Write down the equation of the vertical asymptote. Well, remember that the vertical asymptote, you can look at the prohibited value, x is not equal to 0, and that is exactly the vertical asymptote, because the definition of the vertical asymptote is the value not taken on by the function. So when you prohibit a value like that, that is the first vertical asymptote. So the vertical asymptote, the function is going to be x equals 0, which is the opposite of x is not equal to 0, right? Okay, now we're going to look for the horizontal asymptote. Remember, to find the horizontal asymptote from the last chapter, you go to second table, and then you just kind of like zoom out in either direction and then see what value you're approaching. What whole number are we approaching? The reason why I say whole number is because in math studies, usually the asymptote is a whole number. Okay. We're approaching 22. In fact, we reached 22. Oh, we're passing 22. Now we're going lower than 22. It's 21. Okay, and then actually the value turns out to be 21. If you go out to like 500 or so, you'll finally see that it doesn't go past 21. Okay, so the horizontal asymptote is y equals 21. Right, remember you always write y equals to introduce the horizontal asymptote because it's an equation of the horizontal asymptote, so it has to have an equal sign in it. Write down the room temperature. Oh, by the way, there's a trick here. If you know that the horizontal asymptote is 21, you can go back and look at your function. If your function is written in this format, look, the 21's right there. Okay? It's not always going to appear in the function because sometimes it's not written in this format. Like, for example, and I won't go into this in detail, but if you wanted to, you could write this exact function 21x plus 79 divided by x. And this is actually the same thing. And if it's written in this format, you can't tell where the asymptote is as easily as before, right? So be careful with that. But in this case, since they have an isolated constant here, that is the asymptote, just like in our exponential unit days, okay? By the way, the horizontal asymptote for a coffee or water cooling in a room problem, the room temperature is the horizontal asymptote, because if you have your Starbucks coffee sitting in a room that's 24 degrees air conditioned, guess what the temperature of your coffee is going to be in about 2 hours? It's going to be the same temperature as you set the air conditioning. Okay? The air conditioning is going to set the temperature of your coffee too. So the room temperature is going to be 21 degrees. Alright. Number 2. Oil is heated on the stove. The temperature is modeled by this function, 100 minus 100 divided by x. X is not equal to 0, where x is the time in minutes from when the oil began to heat, and f of x represents the temperature in degrees Celsius. Use your GDC to sketch the graph of the function for 0 to 50. Okay, guess what's the first thing you do? You type it in. 100 minus, put in parentheses, 100 divided by x. We put parentheses around the fraction again. It's always good to do. Clear that out. We want to graph it from 0 to 50, so we use window. And we'll graph, and then maybe we're going to have to adjust the, oh, yeah, that looks pretty good. We don't need to change the zoom fit necessarily. Okay, so we graphed it, and it kind of looks like this. All right. Actually, it doesn't, I drew it so that it comes out at 0. It doesn't really do that. It's like comes out a little bit to the right of 0, right? Find the temperature of the oil after 10 minutes. So you could do that with trace 10. And the temperature is 90. Okay, and the other way you could do that is with second table. And you could look for the value x equals 10. And then it says find the number of minutes it takes for the temperature to reach 30 degrees C. We're going to 10 here. Oops, I passed it. X equals 10 is 90. Hey, what do you know? Same thing as when you do trace. Find the number of minutes that it takes the temperature to reach 30 C. Where does it reach 30 C? Here it's already hotter than 30 C, so we're going back down a little bit. Oh, there we go. It's between 1 and 2. Okay, so there's a couple ways to do it. Remember, you could do plus, here you could do plus 1, and we could break it down. The more elegant method is you go to y equals, and for y2, I'm going to put the value of y that we look for, y equals 30. And then I'm going to graph it. Oh, and look at that. The y equals 30 value is so small that you can just like barely see it down here. So let's do zoom fit again, like I said that we didn't need to, but now it's probably a good time to do it. Zoom fit, remember, is option 0. That's a little better. Okay, oh, there we go. That's much better. Okay, so now we know that this is the level 30, and then we want to know when it reaches 30. It's right there, so let's use second calc intersect, and then we'll find out when it hits 30. First curve, yes. Second curve, yes. When do you actually need to be careful about hitting enter after first curve and second curve? If you have more than 3 curves in your calculator, then you need to be careful about which ones you're picking. We did that in an investigation before. When you only have 2 curves in the calculator, very convenient. There's only 2 curves, so it doesn't matter. You just hit enter twice. Guess. Does it matter what you put for guess? Not for this one, because there's only one intersection point. If there's more than one intersection point, you have to be careful about where you put the cursor. You have to put the cursor close to the intersection point. So we can see here that x equals 1.43. So the number of minutes it takes for the temperature to reach 30 degrees is 1.43. Write down the maximum temperature that the oil can reach. Okay, we could do that with trace. We could just like travel here along the line, see what y equals. Looks like it equals 97, 98, 98, okay? So it's approaching some number. We're not sure what number. Actually, it's approaching the horizontal asymptote, which we can identify as 100 because it's got 100 there. But you could go way down and see when it reaches 100. Can we do that with trace? Maybe we could say trace 1,000. No, it doesn't let us do that. We would have to adjust the graph so that it actually showed that much. Okay, so you could do that by, going way up or way down to see that it approaches 100. So it looks like you need to go pretty far. Okay, so maybe one of the things you could do is you could change window size. You could say, hey, I'm gonna go between 0 and like 500. Graph it, and then I'll use trace now. Oops. I don't need that second function anymore. And I'm going to do zoom fit. Zoom. 0. Okay, and then I'm going to do trace. I'm just going to go way down here. Do you see how it's getting very close to 100? 99.75 here. Okay, so it's approaching 100. Hey, what do you know? 100. That's 100 too, right? So the maximum temperature the oil can reach is the same as the horizontal asymptote, which is going to be 100 degrees. Okay, you can say like 99.9999. All right? Okay. Number 3. Use your GDC to sketch this graph, 5 over x squared. It's kind of a weird graph. Different than what we've been graphing. We could put parentheses. In this case, it doesn't really matter, but that's okay. Better to have more parentheses than you need. 5 divided by x squared, and then we're going to graph it. And we're going to graph it, it doesn't say from where to graph it. So let's just do zoom standard. Zoom standard is option 6. Okay. So we can see that it goes up on both sides instead of normally a hyperbola goes up on one side, goes down on the other side. This one goes up on both sides. Okay, so it says write down the values of x when y equals 8. Okay, so remember there's 2 ways to do that. One is you can do second table and set the step size to be really small. The other is you can go to y equals and then you could put the second function in the calculator and you're going to say that the second function will be y equals 8. And then you're going to graph it and then you're going to see when they intersect by doing second calc intersect, which is option 5. First curve, yes. Second curve, oops. First curve, yes. Oh, you know why it does that? Because it's on the asymptote of 0, so you need to move the cursor off to the side a little bit. Hit enter twice. Yes. And in this case, we want the left intersection first, so we move the cursor to the left a little bit. We hit enter. We get negative 0.791. Negative 0.791. And then on the other side, we'll do the same thing again. Second calc, intersect, except now we're going to move the cursor a little bit. Oh, we're going to first curve, yes. Second curve, yes. And then the guess this time is going to be a little bit to the right. And then the intersection is 0.791, positive 0.791. So the first one was negative 0.791. The second one is positive 0.791. Okay. And let's sketch the graph. It looks kind of like this. Alright? Okay. Write down the equations of the vertical and horizontal asymptotes to the graph. Okay. So the vertical asymptote is obviously the opposite of that, so it's going to be x equals 0. Did I say vertical asymptote or horizontal asymptote? I meant vertical asymptote. What is the horizontal asymptote? Well, it looks like it's approaching like 0 or something here. We could use trace, And we could do that. We just zoom out here, and you see how it's getting smaller and smaller, 0.09, etc. So you could see that it is going towards 0. The other way you could do is you could do second table, and you could zoom out in either direction. I'm going to zoom out in the negative direction. You can see how small it's getting close to 0. Okay. So since it's getting close to 0, the horizontal asymptote is 0. We say y equals 0. Okay. So that's it for page, is that page 4? Page 4.